So now let's get into some actual transition metal complexes. So when we start dealing with transition metals and throughout the quarter, we're going to be obviously talking a lot about transition metals. They have very different types of bonding patterns than we're used to seeing. They have much higher coordination numbers. They have access to different geometries, and pretty much all this new kind of phenomena to observe, as I alluded to in our intro video, is due to the fact that these have access to d orbitals. And so, in order to better understand these shapes that we can access, we need to be able to draw and understand these d orbitals. Just they need to be second nature, right? If I asked you to draw a p orbital or an s orbital, you'd probably get those shapes down very quickly. Similarly, you need to be comfortable with the d orbitals. So again, there are 5 of them, and they kind of fall in 2 separate classes. And so we can draw our 3-dimensional axes here, right? We have to be able to comfortably draw these orbital shapes in order to understand kind of the 3-dimensional implications of them. And so for these axes, right, we can label our x, y, and z. Labeling these coordinates is kind of arbitrary, but it can be important. Um, and we will see in a second why these or how these labels come into play. So x, y, and z, almost done here. X, y, and z. So our first few orbitals, d orbitals kind of have generally like a clover-like shape. And so we can see for this first set that I'm going to draw, right, it kind of has this clover shape. And we want to make sure we pay attention to the shading of the lobes. For the d orbitals, the opposite sides are shaded the same way. And in this case, we can see that this is in the YZ plane. And so this orbital is named DYZ. And what we're going to see for these first 3 is they are just labeled based upon this plane that they are located in. So it might be helpful if you go online, you could find better pictures of these and you allow them and you can rotate them. But you have to be able to draw these and you need to practice understanding their 3-dimensional shape. So like I said, we kind of have some trends here for the first 3. So there's also the same fundamental shape that is in the XZ plane, right? So I tried to get this where it's rotated a little bit and it's in this XZ plane. This is DXZ. So based on what we have so far, I'm going to give you a second, take a second, guess what this third orbital is going to be. Hopefully you guess that this is in fact DXY, right? And this is coming out, right? And we have the same kind of shape, right? It's just oriented in these 3 different planes. And so we want to be able to understand what these shapes are, right, where they come from, but also just be able to draw them because it's going to be really important that we can represent these structures. So I'm out of these, simple planes, and yet I have 2 more d orbitals to account for. And so these have kind of slightly different shapes. And so we'll start with what's called, or one that looks very similar, except it is now aligned on the axis. All right, so this is on top of the XY axis. It still has that kind of clover shape to it. However, it's just directly lined up with the axis. And this is dx squared minus y squared. We're not going to get too far or too deep into why these are the names. These are just going to be the names and what we call them. And the last one is everyone's favorite. So it kind of looks like a p orbital. But in addition to the p orbital shape, it has this fun little donut that goes around it. And the shading of the donut is different than the shading of the orbital. And this is dz squared. So these are our 5 orbitals. And again, you need to practice drawing these over and over so you can get clear representations and clear pictures of these 5 different shapes, right? That's one of our learning objectives for the day is get comfortable with these 5 shapes. So practice and practice and practice until you're very comfortable drawing these and you feel that the 3D representation looks pretty good. So let's move on to our second learning goal for this lecture. So our second learning goal is getting more comfortable with these 3-dimensional shapes, right? So we have 2, 3, 4, 5, 6 coordinate complexes that will be common throughout inorganic chemistry, right? So when we have a coordination number of 2, this is things like water, right? So I'm going to just give some examples. So water, which is bent, right, has a coordination number of 2 around the central atom. We also have things like, acetylene. So using some organic examples, right? And this is linear, but it has a coordination number of 2, just meaning there's 2 things that are bound. Maybe we're looking here, at this carbon atom. So we have some geometries that we're comfortable with for 2 coordinate compounds. We have geometries we're comfortable with for 3 coordinate compounds as well. So something like borane, BH3, right? We know that this is trigonal planar. And something like maybe ammonia. So again, I'm going to put the lone pair on just a stick there. We can use those dashes and wedges, right, to denote this 3-dimensional shape. So electronically, this looks like a tetrahedral shape, but we know that we can't really see those electrons. So as a 3-coordinate complex, right, this is trigonal pyramidal. And then for organic chemistry, we really did top out at 4 coordinate compounds, right? So we have something like methane, CH4. This is the tetrahedral shape. But now that we're getting into inorganic chemistry, as our coordination numbers increase, we have actually different geometries that we can adopt. So one very famous molecule example is called cisplatin. And we'll talk more about bonding in this molecule here in a minute. But this compound is actually square planar. And as we go down the periodic table, what we find out is that the square planar geometry is actually a little bit more common. And it's because this is stabilized through electronic factors. So it has to do with the bonding modes and the molecular orbitals that we can access, and not driven just by sterics, which is where we get the tetrahedral shape. So as we move on to 5 coordinate compounds, right? So 5 coordinate complexes, something like P F5 is actually 5 coordinate. So we have our fluorines. Right. So this is one of our geometries. This is called trigonal bipyramidal because it looks kind of like 2 trigonal pyramids that are stacked base to base. So some additional terminology that's helpful here. This actually has 2 different non-equivalent sets of fluorines. So we have equatorial fluorines that are kind of around the equator of the molecule, and we can see that there's 3 equatorial positions, right? These are equivalent to each other. And then we have axial fluorines. Axial. And so these are chemically different, right? They have different bond lengths in different local environments. So that's just something to keep in mind. But here we have this trigonal bipyramidal shape. We also have some compounds that, for example, in the lab, one thing we normally make is a vanadium complex. And so I'm going to abbreviate the structure here a little bit. Right, and these are actually connected through kind of an organic framework. But this vanadium center here, this would be a square pyramidal geometry. Again, we want to be comfortable not just with the geometry itself, but also being able to draw those dashes and wedges to denote that 3-dimensional shape. So these are the 5 coordinate types of compounds that we can see. And as we move up to 6 coordinate, this is actually probably the most common coordination number that we're going to look at in Chem 481 and even in 484 quite a bit. And for 6 coordinate complexes, these are octahedral in shape. And so one of the examples we'll look at is chromium hexacarbonyl, right? This will be a very common example that we'll kind of dig into as we talk about different features throughout the quarter, right? So these are carbon monoxide that are on here. And again, we'll talk about this kind of orientation, what these actually mean later. But we can see here that there's 6 different things that are bound to that chromium center. And again, the name for this geometry is octahedral. Right, octahedral. And that's because if you were going to connect all these, you would make an 8-faced thing, right? So like it would be like a D8 if you're used to rolling dice around. And so this is an octahedral geometry for 6 coordinate compounds. This is probably the most common type of compound that we're going to work with in 481. It has some nice symmetry. It has some easy to kind of break down and understand orbitals, which makes it fun to kind of dig into. Right, so this is kind of tied in here to learning goal number 2, right? Being able to draw out these 2, 3, 4, 5, and 6 coordinate complexes and getting comfortable with those.